Hello Abaqus user, welcome to Abaqus Acumen for a quick and sound learning. Today's session we are going to do on a rubber seal compression test. Now learning out of this is using a hyperelastic metal model, how to model a hyperelastic metal model in Abaqus. Second thing is how we can define a self contact. So right now if you see during this compression they are not in contact and then there is a self contact, and learning how to do a tie and model using axis symmetry element. And this particular example we are going to do in an Abaqus Standard. So this is an implicit solver, not an explicit solver. So once you do in explicit, it is easy to solve it, but implicit, then you use a self contact, get a stability of model and then model it. And then you can also at the end we can also plot response of rubber seal in terms of force versus displacement. So with that we'll quickly go to the drawing board and we'll just first define the problem. We'll understand how we can do this problem. So today's problem is rubber seal modeling in Abaqus. So we'll model rubber Abaqus seal modeling in Abaqus Standard, mainly getting into a hyperelastic metal model. So before that we'll recommend you to go to our video on the Abaqus hyperelastic metal constant evaluation from the test data. Now lot of in open literature, when you go and look into in like Google or YouTube, you find people give C0, C1 or D different material constants, and these constants represent the hyperelastic metal behavior using a strain energy function. But how we can get those metal constants is important, and for that you need to go get those constants from the test data, which is shown in our earlier video. So we'll strongly recommend to go our first video on hyperelastic metal constant evaluation from test data, so you'll understand how the metal data is evaluated, and then you can come to a example on the hyperelastic metal model. Now we are not going to evaluate the material model here. I already evaluated the constants from the test data, so that will use it directly. So rubber seal, it is a axis symmetry component. So we can, whenever you see something like axis symmetry, take advantage of those. If you are a good analyst, good FE analyst, then go and take the advantage of axis symmetry, whatever you find it. So this is the axis symmetry component, so we'll take the advantage of axis symmetry. We are going to model this using a 4-noded axis symmetry quadrilateral element. So we are going to use CAX4R, and these are the components. So I just put this coordinate so you can easily model the rubber seal. So like this is so if you check, this is OD is 2, and then point this width is 0.4, and total height is 7 millimeter, and then the extreme end OD is a 3.4. So we'll build this, and once you build this, give a fillet. So there is a fillet, you see this fillet which is a 0.2 millimeter. So one thing I forgot here to put the units, so it's Newton, millimeter, second and ton. So mass is in ton, time is in second, Newton, millimeter. So whatever unit you get, stress unit will be MPa. And then this is what exactly I was talking. So rubber property will define using C0, C10, C01 and D. D represent the compressive behavior. In case the D is 0, it's become incompressible component. So there is a compressibility in this rubber, so we put 0.0124, and then the C10 and C0 is calculated from the test data. We'll define static general step with 0.01 initial value, and then this. The important learning it will do a self contact. This will be in Abaqus Standard. And this is a compression setup. We'll have a bottom plate, you'll have bottom plate and then top compression plate. You'll will push this by 3.75 millimeter, and this will be like a tie here. So this will be one tie, this will be tie 2. So there are two ties will be there. So let's start the modeling this. So I'll just remove this and then I'll just set up this with, and then first we'll quickly start building the model. Now we'll first build rubber seal. So when you go to create component, say create and then put rubber seal, and then it's a deformable axis symmetry, and then approximate side 20 we are putting. Anyway, our ID is 2, OD is 3.4, and our height is 7 millimeter. So then we'll just put 0, 0. So I get the center point. Then I put 2, 0. So I get the first point. Then I put 2.1. So I just move up. Then I put 2, 3. Then 2, 5. So first I just concentrate on the inner side. So then I'll put 3, 2. So that way, so this is the one, this is the second, then I got this. So if I just start putting it, this is my 1, 2, 3 point I got. So I'll put some more. Then I'll put 2, 5. So that goes up. Then I'll put 3, 4. So then I'm just connecting them. So then I'll put 3, 7. And I'll put 3, 6. So just try to build, instead of putting all point, we'll just put one by one. Then we'll put 2.4, 2.4, 0. Then 2.4, 2.4, 1. So 2.4, 1, because then it was showing something different. So this I got, and then I'll just put these things, and then we are done. Then I'll put 3.4, 2. I got 1 point. Then I got 2.4, 3. I got other point. Then 3.4, 4. So I'm quickly building this. Then I need to go one more. So I need to get this coordinate, this, then we are done. Then 2.4, 5. 3.4, 6. And 3.4, 7. So I get the top one. So we almost built the So we just built the initial structure. So going back, when you looked like here, so these are the all coordinates. So you can just pause the video, take the coordinates, and then we'll give a fillet. Then the next step is we'll give a fillet. And then put a fillet. 0.2, 0.2, 0.2, 0.2, and then 0.2, and then 0.2. Then you just keep fillet. And that's it, we are done. So we are done with the rubber thing. We'll create a material property now. Now material will be rubber. You go to mechanical, go to elastic, you go to hyper elastic, and if you can do a test data evaluation. In case you don't have, we are going to do mono-rivlin. We are going to go use a coefficient. So coefficient is like, we'll use 0.69. This already I evaluated, so it's easy for you. 0.69, then 0.173, and then D1 will put 0.0124. that is the part, or D is actually the compressibility it is defined, and this is then strain energy function defining your hyperelastic material. So this three parameter is nothing. Hyperelastic material model you cannot define using Young's modulus and Poisson's ratio. You need to define this using a strain energy function. So we have done this. We'll define, this is axis symmetry, so it is a solid. We'll define rubber, that's it, and then we'll just assign this. So once you assign the section to them, it will change the color. So we have done that. Now other things we'll just quickly do it, because this outer area will be having a self contact, and the bottom we are going to tie, and the top we are going to tie. So we'll just create a surface now, or you can create later on also. Self contact. So this way you can select the first thing, and then you want to continuously select, then you put a shift button. Don't select the top, you take all outer periphery you select. And then you say done. So you created that. We'll also create two more surface. You select top, then you say slave. This will be slave, and then rigid will be master. So this is top, and then you create bottom slave and select the bottom surface. This is going to be tied, so you'll also learn how to do a tie, and that's what actually we have finished. Now we'll create two more component. Will be like, it will be like bottom, and this will be axis symmetry, but it will be discrete rigid. So this will be start from 0, 0 and then 7, 0. So this is the one thing, and you said done. It is done. Once we done this, it is just a line, so it's already understand this is a rigid component, so discrete rigid we are taking, so we need to mesh it. And then other important parameter for the rigid is defining a reference point. So go and select the reference point. So you selected reference point, it is done. Now we'll create the other thing is the top. So you have discrete rigid or analytical rigid. Analytical rigid you don't have to mesh it. For what discrete rigid you have to mesh it. So top axis symmetry, then you select the first point is like 0, 7 and then 7, 7. So you get a top coordinates. Then you just put this. Done. And then reference point you put it here. Now we done this. This top will create the master surface for the tie. So I'll create a surface. This will be master bottom. I select this. So this will show the two arrow. One is magenta and yellow. We want a surface at the top. So I'll select the magenta. And similarly we'll select you click on the bottom and then create surface here. So it's a top and then you say master top and then select that, and then we want inside surface, below surface, so I select a yellow. So we already created the surfaces. Most of the part we are done. Then once part is done, go to the assembly instance and create this instance. So you already have geometry, you have top, bottom, you already given reference point, you created the outer surface set, top surface set, everything is done. Then next step is you will give a step. This will be static analysis. So you give the name rubber seal compression. I generally doesn't put a gap. Sometimes Abaqus solver also gets some issue if there is a gap. So and then static, you give a static, and NL jump on, you again give the name rubber seal compression, and then this will be like 0.01, and then 100. We can reduce this because this is rubber, you get lot of issue to get convert. So once we've done that, we'll go to the interaction. First we'll put a tie. So go to the constraint manager, say tie top. First we'll tie the top. Master surface will be the top surface which already created the set, it will highlight there. Then slave surface will be the rubber top slave, it will also highlight that. Then you just take out this adjust slave node initial position, you just specify tolerance like a 0.1. This is good enough. Adjust slave surface initial position means it will put the slave node on the master surface. Anyway, they are on the same plane, but this creates some distortion in elements. So it's better not to adjust it, but specify the distance, and then it will take care of tying those. Then you create tie bottom, select the bottom master surface, so it is highlighted, and then select the seal bottom slave surface, and then again specify remove the adjust. So you already done a tie. Now we'll define a friction value for contact. So like first select the normally behavior which is default, and the pressure or closure is hard contact, and then select the tangential behavior and give penalty based friction of 0.2, and then we'll define a self contact. Then you create self contact, and you can put initial, so self contact standard. You can put in steps also, but we'll just keep before the step, it doesn't matter. And then I'll select that whole surface. So this is all outer surface we had taken, it's a default friction value, and then you define a contact here. Loads, there will be only two load. We'll just put this as a constraint. So create, so BC1 will be the end caster, so we'll select this bottom one. and put the end caster conditions here. So this is constraint. The other is top movement or compression. This is not in initial. Initially you cannot compress it. You need to use a inside the step you say displacement and rotation, and then select the top one, done, and then you put radial and theta is 0, and this you put minus 3.75. so it will move down by 3.75. once it moved down, and then it will compress it. We'll quickly have a mesh. We'll start with rubber seal. Go to mesh control and select chord and middle axis, which is a free good mesh, and then define something like a 0.08 will be good enough. Select the element type. It might be already selected, but just confirm it. It is selected. CAX4R, it is a axis symmetry element, and then mesh it. So you done that, then you select the top, just put 0.1 so it have good compatibility, and then mesh it. Then we will select what element it is. So it is already selected the discrete rigid, so no issue. Select the bottom one, again put 0.1 and mesh it. So this way you already done it. So I'll just save the file, rubber seal to save. So we already saved the file. Now everything we have done defined. Now only thing is we'll take a reaction force and displacement for this, so we can plot what is the stiffness of rubber seal. So that for that we'll just in history output we'll create history output for not whole model. We'll check for set, but for that we need to have the name. So we'll create one more set. So we'll just create one more set in assembly. Create, will say reaction force RF. Not we'll not use this. We'll just put a reaction force RF, and then we'll select that reference point. It is not a node, it is a reference point. So we've done that, and we'll history output will just create that set, and then select RF. We'll select, and then we'll say we want reaction force 2, and then other thing is we want a displacement. So displacements also we want a 2. So we already asking for output from this is get a reaction force and displacement for this, so you can plot what is the stiffness of the rubber seal. So we've done everything. We'll save the file and we'll submit a job create rubber seal, and then we'll submit it, and we'll just wait for result. Before that we may just check how the input file looks like. Look into input file, how input file looks. So this will give, so the part definition, so you put a, I generally prefer to do this in text pad, so text pad is better. Part, you see the bottom one, then it is rigid, then it have some sets, rubber seal, then you see the element type. You might be seeing this is the axis symmetry element, then you generate it, and then you see the self surface created, element set, then section solid, we have assembly instant 1, instant 2. We will just look into bottom, and then you have this tie, 2 ties. Then you have this, the mooney-rivlin metal constants. You given a friction value, you created a self contact, then it's rubber compression, you put an end caster condition at the bottom, top one is moving, and then history output. So now we've done everything. We'll just wait for results. So results are out. So I'm just looking into how it looks like. So this is in the results is in now axis symmetry. You can see there is no self contact, and then slowly it comes down, it creates self contact, and we'll just plot it in. So what we'll do, we'll just plot it in, we'll sweep this by 180, so we'll have a better view. You can do this type of analysis using axis symmetry, but when you present, you just take the advantage of this sweep thing, and then sweep it and then show it, so people will see it's 3D, and then it's anyway you are representing the 3D, and then you see the self contact happening. There is a tie. Now other important thing is, we'll just quickly measure what is a stiffness of this. So we'll take a history output of reaction force, what we have put. So this was reaction force, what we asked for these two things. We'll just plot it. So since the displacement is in negative direction, so it's negative displacement and negative force, but then when we'll plot it, we'll just multiply with -1. So for that, once you plot it, you just put a XY data manager, or you'll say operation. You just click on XY data, say operate on XY data, continue, and then you select this function called combine. Then you say, you select operator -1, then multiply by x will be the displacement, so this is that, then put a comma, then put -1, multiply, you put this, and then say plot the expression. So this is what exactly it looks. So it start here somewhere, actually the self contact happen. So once the two rings comes in contact, the stiffness suddenly goes up, but then these rings start sliding, then that where stiffness go down and then go up. So this is what is the highest compression force is 2.5 Newton, and then you can put a stiffness like 2.5 divided by displacement, that is your rubber maximum rubber seal stiffness. So whenever you need to calculate the rubber seal spring stiffness, you just go and calculate what is the maximum force divided by displacement. That way you can plot this. So this is where actually the self contact happen and move up. So I think we given a sufficient learning out of this. I hope you can take this learning, take forward in your project or your assignment or industrial assignment. Thanks for watching this video. Don't forget to like us and subscribe. Abaqus Acumen will help Abaqus community to learn fast and quick. Thank you. Bye bye.